In this lesson, we're going to simplify radical expressions. And this is part 2 to the video. These types of problems, they're not going to be perfect squares. They're not going to be perfect cube roots. So we're going to have to figure out how we deal with things that are not perfect squares, perfect cubes. So here's what we're talking about. So first problem is we may be looking at, and we have done 8 examples in the first part. So this is number 9. Where we are trying to simplify the square root of 200. And there's 2 different ways to do this. If you know your perfect squares really well, you can basically apply this property and think, all right, what's the biggest perfect square that I can divide out of 200? And that's 100. And 2 would be the other value. So you can break it into 100 times 2 is the exact same thing as 200. Then you can apply this property where we're going to break it into individual square roots, and you're still going to be multiplying them. And the square root of 100 is 10, and the 2 we can't square root. So that would be it. So another approach to this is taking that 200 and making a factor tree. So let's say we took 10 and 20. This is 2 and 5. This could be a 4 and 5. And I'm going to circle my primes so I don't lose track of what I got. Okay, so if we list this out, we're talking about a 2 times 2 times 2 times a 5 times a 5. All right, so a different approach rather than trying to pull out perfect squares. If we don't know them all that well, we don't know perfect cubes, perfect fourth roots, we don't have to. We can actually look at this, and we're still square rooting, we're looking for pairs. So there's a pair of 2's, there's a pair of 5's. We can take 2 out of the square root. We can take this pair of 2's because really that's 4, and we can square root 4. That's really 25, and we can square root 25. So this can come out of the square root, this can come out of the square root, and these 2 pieces are multiplied together just like anything else is all multiplied together, and then times whatever's left over. So that's square root of 2. The 2 is going to be left over inside the square root because it didn't have a second 2 to pair up with. So we'll combine these, that'll make 10 square root 2. Now you may not need to do that with perfect squares, but maybe when you get to perfect cubes, fourth roots, things like that, it might be nicer to just kind of make a factor tree, see how many you have. All right, so let's do another problem. So if you have the cube root of 64, depends how well you know your perfect cubes. But 64 is a whole bunch of 2's. And it is, 64 is going to be 8 times 8, which is 2 times 4, 2 times 4, 2, 2, 2, 2. So we have 6 2's. So 2 times 2 times 2 times 2 times 2 times 2, you're looking for groups of 3. Here's a group of 3, here's a group of 3. So they can all come out. So that's one group of 3 that can come out. There's another group of 3 that can come out, and you don't have any more pieces that are left over inside the cube root. So that becomes 4. And if you knew your perfect cubes, that is a perfect cube. 64 is a perfect cube because it's 4 times 4 times 4. So the better that you know the perfect squares and perfect cubes, the easier the problems are going to be. But you can always get away with making a factor tree and kind of doing a little bit of the long way. Sometimes you almost have to. So let's do another one. So what if we did the fourth root of 64? Now good news is we already know that it's 6 2's multiplied together. And we're looking for 4 of a kind. So for 4 of a kind, I'm looking for 4 of a kind because we're looking at the fourth root. So that's one group of 2's that can come out, but we're going to have leftovers this time. That's what's left over, and we just need to clump that back together. And that is our answer for the fourth root of 64. That's as simple as we can make it. All right, let's do another one. So if we did the fifth root, we'll throw some variables in this time. Or nope, just some numbers, but they're going to be separated. All right, so you got a 27 times 81. You could clump all this together or kind of take advantage of the fact that they're already broken apart a little bit. And 27 is 3 threes multiplied together. 81 is 4 threes multiplied together. And we're looking for 5. So we're looking for 5 of the same kind. So there's 1, 2, 3, 4, 5. So that is one group of 5. So that can come out because we can take the 5th root of that. And we still have 2 left over. So we'll multiply that back together. And that makes 9. All right. So this time we'll throw in a variable. So if we do the square root of 12a squared b to the 5th. All right, and we're going to try to see what we can take out, what we cannot take out. So 12, we can break that apart into 4 and 3, 2 and 2. So it's 2 times 2 times 3. And going back, we're looking for perfect squares. So here's our pair. So that can come out. We have a 3 left over. So we're still going to have something left inside this square root. For the a's, exact same idea, same concept. We're looking for pairs. Well, we have exactly 2. That means that's one pair that can come out, nothing left over. B to the 5th. Well, we have 5. We're looking for pairs. So if you need to, you're welcome to write it out. And we have exactly 2 pairs with 1 left over. So the pairs can come out. There's 2 of them, and we have 1b left over. So really this just ends up becoming division. You're looking for pairs, you're going to take 5, divide it by 2, and see if you have anything left over. So if you divide it by 2, it goes into it 2 times with 1 left over. It's another way to think of it. All right, we'll do a couple more. So number 14, we'll take the cube root of 16x to the 4th, y to the 6th, and we'll try and simplify that. So 16 is just made up of a bunch of 2's. So 2 times 2 times 2 times 2. And we are looking for 3 of the exact same thing. Here's our pair of 3's, or 3 of a kind, 3 2's. So that can come out. That's going to have to stay inside the cube root still. And I'm going to give some space because I have a feeling some variables are going to come out as well. So x's. We have 4 x's, we need 3. So that's 1 3 of a kind that we can break off of that, but it leaves us with 1 y on the inside. And then y to the 6th is perfect. We need pairs, 3 of a kind. We have 6, so we can take exactly 2 out with nothing left over. So that is as simplified as we can go with that. And the last one. If we did the 4th root of the exact same thing, is that going to change our answer? Absolutely, because we're looking for 4 of a kind, not 3 of a kind anymore. So 16 consists of, again, 2 times 2 times 2 times 2. And then we're looking for 4 of a kind. That's everything. So 16 is a perfect 4th root. So that can come out. And then we have x to the 4th. We're looking for 4. So that's perfect. All of those can come out. And then for the y's, though, we have 6, and we're looking for groups of 4. Well, we have one group of 4 that we can take out, and that means we have leftovers. We have exactly 2 left over. And that simplifies that. So that's part 2 to simplifying radical expressions.